So now we're going to be looking at antiderivatives. Antiderivatives, we've already used this language, but antiderivatives is the opposite of the derivative, or another word for antiderivative is to take the integral, and we've used this language a little bit. So in other words, let's say that I want to take the derivative of x squared. Well, we know that the derivative is 2x. Well, if I wanted to find the antiderivative of 2x, that's saying which function has 2x as its derivative. Well, this would be x squared plus something. Well, plus what? What would be the derivative of x squared plus 5? The derivative of x squared plus 5 is 2x. And the derivative, because the derivative of 5 is just 0. What about the derivative of x squared plus 20? This is also just 2x. So, in other words, the derivative of x squared plus any constant is going to be 2x. So the antiderivative of 2x should be x squared plus some constant that we would need to solve for. So the idea of antiderivatives, it's just it's to find the reverse. It's not to find the derivative, it's to find the function that has, to find the antiderivative of this is the function where this is the derivative. So in other words, if my derivative is x cubed plus x, what must be my function? All right, so working backwards, let's think about this, and we'll develop some rules in a second for this. But working backwards, you know, if when you take the derivative you subtract a power, when you take the antiderivative, you're going to have to add a power. So my function is going to be x to the fourth plus x squared. But when I take the derivative, the power drops. So if I want to have a 1 here and a 4 is going to be dropping, I need to put a 1/4 there so that when the 4 drops, 4 times 1/4 will be 1. Similarly, a 1/2 here. And plus some constant c. Always put this plus some constant c. Well, let's see if this works. Let's see if this in fact works. The derivative is going to be 1/4 times 4 times x cubed plus 1/2 times 2 times x plus 0. And these are just 1. So we get left with x cubed plus x, which is exactly the derivative with which we started. All right, so let's do another one. So if I wanted to find if this is in fact my derivative, then my function, well, if it's x squared now, it would have to be x cubed. What do I need to put in front? Well, for me to have a coefficient of 1, I need to put a 1/3 in front. Minus 4x squared. So leave the constant, but I want to get rid of the power that I'm going to be dropping down, so 1/2 plus c. So this equals 1/3 x cubed minus 2x squared plus c. And now, just to check to make sure that works, let's check it. So the derivative equals, well, 3 times 1/3 is 1, so just x squared minus 4x plus 0. And that's what I should have. What about over here? Well, let's rewrite this 4 sine x plus x to the 1/2. And this is my derivative. So my function itself, well, what has the derivative of sine? What function has a derivative of sine x? We know that cosine x, the derivative of cosine x is negative sine x, so let's put a negative in front to accommodate for the fact that it should be positive. And then plus x to the 3 halves, but I want to have a coefficient of 1, so I'm going to need to put a 2/3 there. And this is done, but let's just check. If I take the derivative, it's -4 times negative sine x plus 2/3 times 3 halves x to the 1 half, which equals 4 sine x plus x to the 1 half. All right, so let's apply this to a problem. It says the brakes on a certain car can produce a constant deceleration of 22 feet per second squared if the car is traveling at 60 miles per hour. So that's its velocity. When the brakes are applied, how far will it travel before coming to a stop? Okay, well, we know that acceleration is -22. Well, acceleration is dv dt. So dv dt equals -22. And this is a constant. This is a constant. And this is the velocity at time equals 0. So if my derivative of the velocity is constant -22, then the velocity is going to equal -22 times t plus some constant. Well, we know at time equals 0, my velocity is 88, so the constant must be 88. So we get that the velocity as a function of time equals -22t plus 88. And just to check, if we took the derivative of this, and this is just a check, if we took the derivative, v prime, we're going to get -22 back, which is what we would expect to get. So we're on the right track. So that's the velocity. How long will it when it comes to a stop? When it comes to a stop, the velocity is going to be 0. So when does the velocity equal 0? That's going to happen when my velocity equation equals 0, or when t equals 88 over 22, which equals 4. So after 4 seconds. So what we want to know is how far will it travel in 4 seconds? Well, given my velocity equation, I could develop an equation for my position, because my position is related to velocity. The change in position with respect to time is my velocity curve. So I know that ds dt, which is velocity, equals -22 t squared plus 88. So my position at any time equals integrating this. Oh, this is just t. Integrating this, I get -11 t squared plus 88t plus some constant. And just to maybe make that even more clear where that comes from, s equals -22, the constant stays, and we have t squared, so we have to put a 1/2 out in front to cancel out the 2 dropping down when we take the derivative. And then we have plus 88t plus a constant, which simplifies to -11t squared, which I had before, plus 88t plus constant. And I want to know how far it travels before coming to a stop. So I want to look at my position at time equals 4 minus my position at time equals 1. And this will be, sorry, my position at time equals 0. So my position at 4 seconds equals minus 11 times 4 squared plus 88 times 4 plus c. And my position at time equals 0 is just c, because negative 11 times 0 squared plus 88 times 0 plus c, which is just c. And finding out s of 4, let me just rely on a calculator for a second. We have negative 11 times 4 squared plus 88 times 4. So 176 plus c. So therefore, the change in my position, which is s of 4 minus s of 0, is going to equal 176 plus c, my position at time equals 4, minus c, which is my position at time equals 0, and that equals just 176. So using integration, using the antiderivatives, I was able to find out, just knowing the acceleration, I was able to find out how far a car went in the time it took for it to stop. So here are the some key rules that you want to start committing to memory. And really, we know that, to take everything on the right-hand side and take the derivative. So if I took the derivative of this, I'm going to get that. And if I took the derivative of this, I get that. Well, similarly, if we integrate, or if we take the antiderivative of the left-hand side, I get the right-hand side. So the one that I want to really pay in particular attention to is that the antiderivative of some function to the nth power, the antiderivative of this is equal x to the n plus 1, because now we're adding a power to take the antiderivative, and then 1 over n plus 1. And the 1 over n plus 1 is so that when this does drop down, it would cancel out to be a coefficient of 1. So the rest of these, what I suggest, put these in your notes, and as you kind of work with these further, you'll really start seeing how connected they are. I mean, it's really just doing the derivative backwards. Okay, that's it.